Hello, I'm David Chadwick, the CEO of Verifiable Credentials Limited. Prior to this, I was Professor of Information Systems Security at the University of Kent, where my last project was to look at the commercial possibilities of verifiable credentials under a UK Innovate project. And because of the success of that project, the university created this spin-out company, and I left the university in February of this year, where I'm now just an emeritus professor. For the last 4 years or so, I've been an invited expert to W3C Verifiable Credentials Working Group, and I'm a co-author of the Verifiable Credentials Recommendation, as well as the implementation guidelines. So I've used my research experience of the last 20 years or so to create the Verifiable Credentials system that I'm going to show you now. I'm going to talk about the way that FIDO and verifiable credentials can work together. FIDO stands for Fast Identity Online, and this was first specified by the FIDO Alliance, and because of the success of their work, they took it to the W3C for standardization, where it was published as a W3C recommendation in 2019, just before the Verifiable Credentials recommendation was published. These two recommendations work together very nicely, because FIDO provides strong authentication, whereas verifiable credentials provide strong identification and strong authorization. So together you've got a very nice coupling to create the internet identity layer. And we'll look at the unique advantages of integrating these two standards together. And then we'll have a demonstration of an application of our infrastructure to a local government use case, and I'll summarize the talk at the end. FIDO, as I said, was created by the FIDO Alliance, and it was published in 2014. It uses asymmetric encryption with a unique key pair created for every website the user visits. So this is quite interesting, that the user has a different key pair in his device or on his key fob for every website he talks to. So this gives the user quite good privacy protection, because the websites can't correlate together who's talking to them, because each one gets a different public key for the user. The FIDO had two original specifications. UAF, the Universal Authentication Framework, was for FIDO-enabled smart devices like Android phones, and then U2F was for two-factor authentication for a hardware device that wasn't FIDO enabled, but you could use a plug-in small hardware token like a USB stick that would give you the FIDO authentication for that non-FIDO device. The same origin policy is a security mechanism to stop web browsers from downloading malicious content from one site to another. It was specified in 2011 in RFC 6454. And when browsers have implemented the same origin policy, then they will only download documents from the same website, meaning a website's got the same origin, and it has the same origin if the protocol, such as HTTP, and the host, which is their DNS name, and their port are identical. So in these two examples here, you can see that some site docx is the same as some site :80, because port 80 is the default port for the protocol HTTP. But HTTPS some site is not the same origin because it's a different protocol. Now FIDO has implemented the same origin policy in a special way. First of all, it mandates that the protocol must be HTTPS, so it doesn't check what the port is as long as it's a HTTPS call, and it requires the host name to be the same. Looking now at the FIDO UF architecture, we've got on the left-hand side the user's FIDO-ready smart device, and on the right-hand side we've got a relying party that the user wants to authenticate to. On the left-hand side, the user's authenticator will generate new key pairs for every website that the user talks to when requested to by the website during the registration phase. So the authenticator will ask the user to confirm the creation of the key pair by the user either using their fingerprint or face recognition or entering a PIN to show that they're there, and they agree to the key pair being created. The new key pair will be created. The private key is held in the hardware. The public key is digitally signed by the attestation key of the manufacturer, and the manufacturer put that attestation key into the hardware when it was created. And the FIDO specification recommended that the manufacturer should put the same attestation key into maybe 1,000 or 2,000 hardwares, so that there's no unique correlation between an attestation key and a user's key. When the relying party receives the attested key, it can validate that it was signed by a genuine attestation key, because the FIDO metadata service contains all the attestation certificates of the genuine FIDO manufacturers. So it knows it's got a genuine public key from a genuine FIDO authenticator. It can store it in its database, and the next time the user signs a challenge with his private key or her private key, then the relying party knows that it's the same device and it's the same user, because the user was authenticated to the device via their PIN or biometric. Now, there are two protocols in FIDO, as I alluded to in the last slide. The first one's registration, whereby the relying party sends a challenge from the FIDO server to the client in the user's computer, and the authenticator creates a key pair specifically for this relying party, and then it asks the user to confirm. Now, this is part of what's known as a user ceremony. User ceremonies were invented by Carl Ellison. He first published them many years ago, and the idea was that we want an end-to-end protocol from the user to the other side. We don't want a protocol that stops at the computer, because if it stops at the computer, we're not involving the user, and we can't be sure who the user is that's using the device. But with a ceremony, we try and make sure we know it's the user, and so FIDO integrates a ceremony into its end-to-end protocol by requiring the user to present a biometric which identifies the user in order to access the private key, which then verifies the device to the relying party. So we've got this end-to-end, if you like, protocol stroke ceremony from the user through his device to the relying party, and all of them have to be in place for the protocol to work. So after registration, the FIDO server has got the public key along with the user's username, and we'll look at that in a bit later. And then in authentication, the FIDO client identifies the user with the username. The server picks up the public key, sends a challenge to the user's device. The user swipes his finger or his face ID on the device to say, yes, it's okay to release my private key to this site, and then it signs the challenge with the private key, and the user is then authenticated to the remote site. Now, the important thing to note about FIDO is that it's only authenticating the user, and it's saying that this user has a public key and it's the same public key every time, and the device has ensured it's the same user every time. But it doesn't identify the user. At registration, the relying party either already knows the identity of the user because it's got the user in its database, and so it requires the user to present some secret information to prove it's him. So, for example, when I first registered to do my tax return online, the government sent to me some letters through the post containing a one-time password and a long random username, and it said, go to this URL, type this secret information into your website, and then we'll know it's you because we've got all your identity information in the database, and that will allow us to tie you together. So that's one way that a relying party can identify the user, by sending the user some secret information and getting him to log in using that secret information. And then FIDO will create a key pair in the user's device, pass the public key over to the relying party, and the relying party can say, well, I've already authenticated, I know who you are, I've identified you, so I'm going to put this public key with you, so the next time you come back, you just need to sign a challenge with your private key, and I'll know it's you because I've got your public key stored. Now, if the relying party doesn't know who the user is, then the relying party might ask the user to self-assert their identity, or this is where verifiable credentials would come in, because the relying party will say, I don't know who you are, present some verifiable credentials to identify yourself. I can then identify you, and now I can ask your device to create a key pair, and I will store the public key, and then when you come back you only need to sign a challenge with your private key, and then I know who you are. Verifiable credentials is a much simpler data model than the FIDO one. Essentially, there are only three components in a verifiable credentials data model. There's the issuer, which could be the NHS, could be issuing tokens to people, it could be issuing health records, it could be issuing employment records, it could be issuing COVID certificates, it could be issuing lots of things, could the NHS. And it issues them to the user, who stores them on his device in his wallet, and then when he's got the credentials in his wallet, he then presents them to different verifiers that trust the issuer. Now, obviously, NHS is one of the most trusted entities in the whole of the UK. And so the NHS makes an ideal verifiable credential issue because everybody trusts it. So obviously the rest of the hospitals in the UK will trust it, but shops will trust it, passenger transport will trust it, businesses will trust it, banks will trust it. So the NHS is in a really strong position to act as an issuer and to capitalise on that fact using the verifiable credentials data model. Now you'll see at the bottom of the picture is something called an optional verifiable data registry. This is where we store all common information, meta information about the system, such as what schemas we're using, what are the public keys of the issuers, and what are the identifiers if we use identifiers of them, etc. And this allows all the components, the three components, to actually have a common understanding of the metadata. Now, the Verifiable Credential Data Registry is optional because you don't actually need some third-party registry running in the cloud. You can actually configure the end systems with this metadata. And many systems today do work via configuration files where they configure the metadata in. But if you have some external registry that you can download information from, that will perhaps simplify the registration, simplify the configuration of your systems, but you've then got to run a verifiable data registry. The important point to note about the VC model is that blockchains and DIDs are not part of the verifiable credentials data model. In fact, this text here, which is in italics, has been copied from the verifiable credentials data model recommendation. I'll read it out to you. DIDs are not necessary for verifiable credentials to be useful. Specifically, verifiable credentials do not depend on DIDs, and DIDs do not depend on verifiable credentials. So anyone who tells you that in order to run a verifiable credential and self-sovereign identity infrastructure, you need to have distributed identities or DIDs, they're actually not telling you the truth, because you don't. And we've proven it because our VC ecosystem, which is built with FIDO, doesn't use DIDs and blockchains. And we don't believe they actually add value for money. We think they're an unnecessary overhead and add to the total cost of ownership. The first prototype that we built with FIDO and verifiable credentials, it was a pre-standard model, was built with some colleagues from the University of Toulouse, and we used a use case that was provided by Dr. Manri Nijar, that some of you might know, and it involved patients interacting with a hospital, booking an appointment online, cancelling an appointment online, because as you know, a lot of money is lost through people not turning up for appointments because they didn't bother cancelling them, and then ordering repeat prescription drugs online so that the patient only needs to make one trip to the hospital to pick up the drugs. He or she doesn't need to come to the hospital, hand in their prescription, and then come back sometime later to pick up their drugs. We carried out user trials at Southampton University Hospital one afternoon with whichever patients turned up to see the consultant, and we gave them the app on the mobile phone, and we said, would you like to test this app? Would you like to practice booking an appointment, cancel an appointment, and ordering repeat prescription drugs? And then will you fill in a questionnaire and tell us what you thought about the app? And the results are published in this paper last year in IEEE Communication Standards magazine. And the results were really very, very positive. We actually had 10 patients we interviewed in the afternoon, ranging from under 20 to over 80. In fact, we had a patient in every decile. And they unanimously found the app easy to use. and 9 out of 10 liked the use of fingerprints rather than using usernames and passwords, and one user said they would prefer voice or iris scanning instead of fingerprints. And 9 out of 10 said they'd always use the app if it was made available to them. So we were really encouraged with this, and then we were looking for ways to be able to build a more standard conforming system once the standard was published. Standard, as I said, was published in last year in 2019, and it unifies UAF and U2F into one solution, and it has two protocols. There's the Web Authentication protocol for web browsers and web servers, and this is actually supported by all the major browsers now, so every browser supports FIDO2, Chrome, Firefox, Edge, Safari. And then there's a lower level protocol which operates between a device and an external security key store, or what's called a roaming authenticator. So if you got your keys on a USB stick, you could use that to authenticate you to a device that perhaps doesn't have an authenticator, and use the CTAP protocol. But we don't use that in our implementation. This is a picture of the Web Authentication API taken out of the standard, and it shows how it actually works. So you've got the relying party remotely over the internet somewhere. You've got your browser running on your computer, which has got an authenticator attached, which might be external or internal. And the Web Authentication API has been implemented by the browser, and the relying party downloads some JavaScript into your browser, which calls the Web Authentication API. This is the registration flow, where it sends a challenge to the authenticator, and the authenticator creates a new key pair. It asks for user verification to create this new key pair, and then it attests the key and sends the new public key and the attestation back to the relying party. Now, the attestation, as I said, in the UAF had to be done by the manufacturer placing an attestation key pair into the hardware. But in the Web Authentication standard, the attestation has been relaxed somewhat. So it can be the attestation by the manufacturer's key placed in the hardware, or it can be self-attestation, meaning that the authenticator is creating a key pair and then it's signing the key pair itself to prove that it owns the private key for the public key, and then sending that back. And because we've got a TLS link all the way between the relying party and the browser, then that is seen to be secure enough for most applications. The one of the things that the attestation by the manufacturer does is it actually provides details of the authenticator, what make and model it is, and that might be important for some applications. They may, for a banking application, they might want to know what model of phone you're using and what level of what's the hardware on the phone, etc., which can be sent along with the attestation. This is another picture of the architecture taken from some other FIDO documentation. It's just a different way of looking at the previous diagram. So we can see here we've got the relying party application, which is JavaScript, calls the web browser via the Web Authentication API, which calls the FIDO2 platform, which then asks the user, do you want to use an external key, an external roaming key to create your key pair, or do you want to use an internal one? And the user can choose which one to use, and that goes over then to the relying party, who will have got some FIDO server software running, and there's quite a lot of open source FIDO2 libraries around, so if you want to build your own FIDO2 server, you can do that quite easily. This is a picture of our VC FIDO2 architecture, which is very similar to the previous diagram, but there are a number of minor changes which I'll point out to you now. First of all, you'll see that the browser has been replaced by our VC holder app. So that takes the place of the browser, and so the issuer application will send scripts across which will call our holder API. So we've replaced the Web Authentication API with our holder API, and that has similar functionality whereby you can register, and but you can also request verifiable credentials to be created to be given to a remote verifier. You'll also notice that there is no external authenticator in this. This is because we do not allow it for security reasons, which I'll explain in the next slide. Then we've got the VC middleware issuer protocol that talks between our holder and issuer. That's very similar to the FIDO protocol, but we've added some extra things in it to support verifiable credentials. So it's basically the web authentication protocol with verifiable credentials added to it. And then on the issuer side, you'll see there's an issuing API which connects our issuing service to the issuer's database. So our assumption is that every issuer that's going to issue verifiable credentials already knows who the users are. The users are held in a database. It might be an LDAP database, SQL database, or whatever. By implementing our simple to use API, they can provide the details about the user to our VC issuer service, and then that will take care of all the security and cryptography. It will actually make the FIDO links, and it will create the verifiable credentials and send those across to the holder, and the issuer doesn't need to worry about that. So the issuer software will run in the issuer's site under its control, but it will do all the crypto, etc. for it. Now, how do we set the FIDO2 parameters? First of all, we mandate that the user is present. So we set the parameter to mandate that because we want to stop automatic issuing of verifiable credentials without the user being aware that the system is doing it, in case he had some malware on his device which wanted to masquerade as a user and somehow tricked our software into issuing it. That wouldn't work because we mandate that the user is present. The other thing is we mandate the use of the platform authenticator. We do not allow external keys to be plugged in. And the reason we do this is to stop multiple users colluding together and pretending to be a single user. So you could imagine that if multiple users had used one device and registered with different issuers and stored their FIDO keys on different external authenticators, then they might bandy together to go to a verifier and pretend that all of these verifiable credentials belong to the same person because they're each putting their device in, unlocking their keys and getting their verifiable credentials. So we stop that, and we require all the keys to be in one authenticator and only managed by one user. And then the final one is we mandate verification to the platform by that one user, typically via biometrics, and that's stopping anyone else stealing the person's device and trying to steal their keys or verifiable credentials. This is a picture of our overall infrastructure, which is looking at not only now the issuing, but also the verification. So you'll see that on the left-hand side, we've got the identity provider with its database that calls us via the issuing API. We've got our issuers that transfer verifiable credentials via FIDO to our holder. And then we've got the application layer between the user and the relying party. And we don't specify what that application layer is. It can be any application that you want. It can be an IoT application, smart car application, a government application. The two application layers we've implemented ourselves are a web browser talking to a web server using HTTPS, and we've also implemented QR codes whereby the relying party displays a QR code and the user can also display QR codes. So we've got an application layer built on QR codes as well. But you can essentially define whatever application layer you want, and you just call our two APIs, the holder API to get the verifiable credentials as a verifiable presentation, and then our verifier API, which takes all the crypto and verifies it and then gives a granted or denied response to the relying party. The other thing we actually have in our protocol is a policy, and the relying party, when it makes contact with the user, says well, first of all, the user says, I want to access one of your resources, and the relying party says, in order to access my resource, you need to fulfill my policy. And the policy is transferred to the user, and then our holder software looks at the policy, it looks at all the VC skeletons that are stored in the wallet and says, am I able to fulfill this policy? Do I have the requisite VCs that are needed in order to get access to the relying party? If the answer is yes, it then gets freshly minted VCs issued from the VC issuer, submitted to the user's device, packaged up as a verifiable presentation, and then transferred to the relying party in the application layer. The relying party is then running our verifier software at its website, and it says to our software, hey, I've got this crypto package of called a verifiable presentation, no idea what to do with it, but this is my policy, can you validate it? And then our verifier software looks at the policy, looks at the verifiable presentation that's been passed over and says, does it match or not? And if it does, it says, yep, granted, you should allow the user access now because he's fulfilled your policy, or denied, no, what is presented does not fulfill your policy and don't allow the user to have access. And also, besides giving a granted or denied reply to the relying party, it also says, if you want, here are also all the verified attributes that the user has sent to us. So I'll summarize our mode of operation from the previous diagram. So there's two modes, really. There's the registration for verifiable credentials, and then there's the use of verifiable credentials. So during the registration phase, the user registers with VC issuers using the FIDO2 protocol, generates keys for each of the issuers, and then the issuers provide the user with what we call VC skeletons. These are not full VCs because they're not digitally signed, but they tell the user what their VCs may contain when they are issued on demand for the various relying parties. The user looks at these contents and then consents to them being issued. So the issuer is getting consent from the user for verifiable credentials to be created and to be given to him when he needs them. Then during the use phase, the user's application contacts the service provider's application. The service provider sends its policy to the user. This policy says which VCs it requires containing which identity information, and then our holder checks the policy against the VC skeletons, and assuming it matches, it then asks the various VC issuers to issue short-lived verifiable credentials on demand for the service provider containing only those attributes that the service provider requires. And this is how we implement selective disclosure. So each of our verifiable credentials that are created on demand are already selectively disclosed to provide the service provider with just that information they require. And this allows the service provider to conform to GDPR. So what are the advantages of our FIDO2 and VC infrastructure? First of all, there's no non-standard blockchain or revocation system needed. We don't need blockchains to store anything because we're using the X509 trust infrastructure, and we don't need a revocation system because we are issuing short-lived verifiable credentials on demand, which is actually how OpenID Connect and SAML work today in federated identity management systems. They issue short-lived assertions on demand, and they don't need revocation systems. That seems to be the best mode of operation in our opinion, rather than issuing long-lived verifiable credentials that then need to be revoked. And this reduces the administrative overhead and cost of running these services because you don't need those two services. So it's a greener, more sustainable solution, we believe. We use the existing X509 trust infrastructure, which everyone is familiar with, and we don't use difficult to use distributed identifiers, which are known to be hard to use and which rely on anyway X509 DNS to map their well-known issuers into their DIDs. So we think this is rather a pointless step. Why map the user-friendly DNS names that people already know about into some opaque DID in order to trust them when you actually trust them anyway via their DNS name? We also use the latest state-of-the-art cryptography for signing our VCs and verifiable presentations, which is JSON Web Tokens. This is the same technology which is used by OpenID Connect today. We don't use bleeding edge zero knowledge proofs, which are much more complex to compute than JSON Web Tokens. And the FIDO2 manages the keys for the user, and the user isn't really aware that they're using cryptographic keys. They're aware that they have to swipe their biometric in order to access things, but that's it. And they don't need to use usernames and passwords because these cryptographic keys are used in their place. And we force the user to authenticate to the device and stop key sharing. So overall, we believe our system has a lower total cost of ownership than competing systems. What we're going to do now is have a demonstration of buying a car parking permit online from a local council. So in order to purchase a car parking permit, you need to prove to the council that you own the car for which you want the permit. And so for that, you would need a verifiable credential from DVLA. You need to have a credit card to pay, and from that you'll have a verifiable credential from a bank. And you also need to prove you live at the address that you want the car parking permit for. And so here we assume we've got a verifiable credential from the council. So those three together form the council's policy, and that policy will be sent to the user when they want to buy the car parking permit, and the policy will say in order to buy the car parking permit you need to present these verifiable credentials. Now in the demonstration the assumption is the user's already registered and he's got 3 credit cards in his wallet. He's got an Amex card, a Visa card and a Mastercard. He owns 2 cars. He's obviously quite a rich user, and he's got 2 verifiable credentials from DVLA for his 2 cars, and he's got an address verifiable credential from his local council. And these skeletons are all stored in the wallet on the user's mobile phone. So now we'll have the demonstration. So this is the demo of purchasing a car parking permit online. The user has got a very modern iPhone that's got Face ID recognition, and he's using the browser on his iPhone to go to the Kent County Council website where you can buy car parking permits. So he's on the website now and he's reading the details. Now this demo goes very quick because the whole thing's over really quickly, which shows how simple it is to use verifiable credentials to do complicated things. So I'll start the demo off, and then I'll pause it occasionally to explain what's happening. So at the moment the user is reading the site, he's reading the top, he says, okay, I need these 3 things. He's going to open his wallet up to do it, and straight away his wallet got the policy from the car parking site, and the policy said, as we saw in the previous slide, that you need a credit card and you need an address from the council and you need a car proof of car from DVLA. And this user's got 3 credit cards. He's got an American Express card, a Visa card and a Mastercard, and as he clicks on each one to decide which one to send, he sees the number appear in the screen below. So the screen is showing him these are the details that the Kent County Council are actually asking for. So he's flicking through and looking at what the details are. Oh, it's that credit card, that one. Okay, I'll choose the American Express. Now he looks through what's the details, the address. Okay, that's fine. And then he looks at his 2 cars. He's got a Rolls Royce and he's got a Ford, and he decides to send the Rolls Royce. And now let's just stop again. What's happening now is that he matched the policy. The holder software then sends off via FIDO2 to the 3 issuers to say, please give me the American card detail, the number, please give me the address from the council, and please give me the Rolls-Royce DVLA details. And the user has to flick on 3 Face IDs. He has to recognize 3 times because he's opening up 3 different FIDO keys. So each time he has to agree to that. So that's why there were Face IDs flicking up 3 times. And that's the 3rd time. And then he goes back to the website, and the website verifies the verifiable presentation, displays the details it's got, and says it's all successful and it's worked. In the following demo, we're going to register for a verifiable credential from a bank. And the assumption is that the bank has already sent us some secret information out of band to our home containing a one-time password, and that's what we'll have to enter to the bank's website in order to identify ourselves. I'm now going to give you a demonstration of registering for verifiable credentials on your mobile phone. The version I'm using is for an iPhone. My iPhone's rather old because it doesn't yet support Face ID, it only supports fingerprint recognition, but nevertheless the software works on all the iPhones. So I've gone to the bank's website and I read that I'm on the right page for getting my credential. So I press the continue button, and now it's asking me to enter the username and one-time password that was sent to my home by letter. Now just stop here a minute. It doesn't have to be a username and one-time password. It could actually be whatever secret information the bank decides it's going to send to you, but in this particular case we're using for the demo a username and one-time password. Once I've typed that information in, what will happen next is that the mobile phone app will make a connection to the issuer, and it will actually create a key pair specifically for the issuer, and it will pop up with a message asking me if I want to create that username for and keep. It doesn't actually say key pair, but it asks if I want to create the username in the key store for that for this issuer, and then I put my fingerprint on it to OK it, and that reads my fingerprint, and then it allows the public key to go over to the issuer's site. It all happens rather quickly. Now, what's happening here is that it's fetched the details of the verifiable credentials from the bank, and in this case I happen to have two credit cards, a Visa card and a Mastercard, and I consent to the bank issuing me these electronic credentials on my card. But before I do that, I want to know what am I signing up to. So by pressing the edit button, I can actually look at the contents of the verifiable credential. And if I don't like the contents, I can remove them and say I don't want those to be in my credentials. So we'll look at the Visa card and just pause a minute. You can see here it's got my the type of card, when it expires, the number and the name. And if I wanted my name to be removed, I could click the tick and it would take my name off, and then my verifiable credential would never contain my name, regardless of whether the verifier wanted it or not. It just wouldn't be there. So I'm totally in control of all the attributes that will go in my verifiable credential. Then next I look at my Mastercard, see what the information is in there, and I'm happy with that. So I then press the consent button, and that's it. It's finished. So it's a very, very simple process, making the user totally in control. Now, what you'll have seen from those demos is a couple of things. One is the user is totally in control of what is going to be placed in his verifiable credentials. The other is that the verifier selectively discloses what he wants to be submitted to itself. And in the particular example, the user had his name and credit card number and expiry time, but the verifier only asked for the credit card number, so that's all that was actually sent. Now, if the user decided that, for example, he didn't want to include a particular attribute in his verifiable credential, but the verifier wanted it, then in that case the transaction couldn't go ahead because the user is refusing to send something that the verifier wants. In that particular case, the user could change his mind. He could re-register with the issuer, which is a function that we support, and on re-registering he could then decide, okay, I will add that attribute next time around, and then I'll be able to access the verifier's website. We now come to summarize what I've been talking about for the last half hour. The advantages of using FIDO2. It's a W3C standard, it's already implemented by all major web browsers, and it's also native to Android and iOS mobile phones. There are many open source FIDO2 libraries that exist for issuers and verifiers, so it's a really easy system to install and use due to its wide support. It allows us to eliminate usernames and passwords between the holder and the issuer and replace them with strong cryptographic keys, which is a big plus in today's world. And it introduces ceremonies between the holder and the device, thereby reducing the chance of someone else accessing the holder's device and ensuring there's an end-to-end connection between the user and the device and the issuer by putting protocol messages in which enforce that ceremony between the holder and the device. Finally, what are the advantages of using verifiable credentials and FIDO2 together? Well, first of all, a secure relationship is established between the issuer and the holder using FIDO2. So this removes the need for usernames and passwords, and it allows the holder to go back to the issuer anytime he wants with a secure connection and ask for verifiable credentials on demand. During registration, we allow the users to be totally in control of which attributes may be inserted into subsequent verifiable credentials, and they consent to their release. So this allows issuers to conform to GDPR. And before accessing any protected resource, the verifier sends its policy to the holder. And this allows the system to issue selectively disclosed credentials to the verifier containing just the properties that they require, which allows them to easily conform to GDPR. And there's no need for a revocation mechanism because these are short-lived verifiable credentials. Finally, the entire system is much simpler to install. than an equivalent one that contains DIDs and blockchains, because we don't need those systems. We just got our issuer system, our holder system, and the apps in the mobile phones. So because it's simpler, it's less likely to have security vulnerabilities and bugs, and it's likely to have a lower total cost of ownership. So thank you very much for listening, and if you have any questions, don't hesitate to ask me or email me with them afterwards. Thank you.